Things were simpler then. Following the Big Bang, there was something instead of nothing. About 95% of that something was hydrogen, which has an atomic weight of 1. One electron encircling a nucleus with 1 proton. About as simple as it gets. 5% of that new something was helium, which has an atomic weight of 2. Beyond that were trace amounts of lithium with an atomic weight of 3. Still pretty simple. Thanks to gravity, these basic elements began to clump together into growing spheres which condensed under great pressure and building heat. Eventually, nuclear fusion ignited the spheres into stars, which transformed the simpler elements into more complex ones like carbon, nitrogen, and oxygen with atomic weights of 6, 7, and 8, respectively. Some of the really massive stars burned through their hydrogen fuel, collapsed, and then exploded as supernova into the more complex elements on the periodic table. A universe-wide march toward increasing complexity was underway. Out of the clouds of newly minted elements, second-generation stars were gathered. From spent second-generation stars came third-generation ones, like Earth's sun. During the latter's formation, 99% of the material within its gravitational reach was swept up. Once ignited into a nuclear furnace, its solar wind pushed the remaining 1% of lighter gases to the outer orbits where they coalesced into the planetary gas giants, Jupiter, Saturn, Uranus, and Neptune. The heavier, rockier remainder, made up of those newly formed complex elements, remained unmoved in closer orbits around the Sun. They gravitationally gathered into the rocky planets Mercury, Mars, Earth, and Venus. Such solar systems added a new structural complexity to the universe, even as the galaxies around which they swirled were themselves gravitationally linked into galactic clusters. The Earth's orbit, in particular, existed in a Goldilocks zone around the warming Sun. It was close enough for water to be kept from freezing into its solid form, ice, and far enough away for it to be kept from evaporating off in its gaseous form, steam. Liquid water allowed various elements to mix into increasingly complex associations until, by one mechanism or another, a combination became self-perpetuating. This represented a new level of complexity, even though it would prove to be a most simple and elemental form of what is called life. From single to multiple-celled organisms, from plants to animals, and from mammals to primates, life on Earth has been a progression of increasing complexity. And so it has been for Homo sapiens, one of many human species, including Homo neanderthalensis, Homo erectus, Homo habilis, and so forth. Having descended from a common ancestor with chimpanzees, with whom sapiens still share 98% of their DNA, humans evolved with larger brains. These cranial organs, which are huge energy soakers, were made possible by the regular use of fire, which allowed for a much more efficient uptake of nutrients through cooking. Larger brains led to advances far beyond those of other species in the animal kingdom, such as more than rudimentary tool making and use. In the case of sapiens, collective learning was far advanced. Knowledge transfer between individuals dramatically expanded social connections well beyond the small circles of their hunter-gatherer forebears. The domestication of animals and crops followed as humans occupied permanent settlements and began to write and diversified their labor as required by towns, cities, and empires. Unable to compete, other human species like the Neanderthals died out along with other large mammals. But the march toward ever-increasing complexity continued on Earth, as it most certainly must have among the estimated 10 trillion Earth-like planets in the observable universe, which are circling their suns in the Goldilocks zone, allowing for liquid water. Ever-increasing complexity has consistently been a feature of the universe ever since the Big Bang. From the myriad forms of matter and life to the intricate structure of galactic superclusters, all are products of the potential bound up in the simplicity of atoms under the influence of forces like gravity. And none of it could have happened without death. The death of stars and the death of species. Death opens up spaces for new forms to evolve as successors to those that have gone before. Although progressing in fits and starts, the trajectory is always an upward trend toward increasing complexity. Over 5 billion species have called Earth home from its beginning to the present, and well over 99% of which have gone extinct. Indeed, the last mass extinction, an asteroid hit, which took out the dinosaurs 65 million years ago, opened the way for mammals to prosper, including Homo sapiens. The latter have risen to the top of the food chain on Earth. This has conferred an unfortunate measure of conceit. Galileo was on the receiving end of it when he defended the Copernican view that the solar system revolved around the sun rather than the Earth. Galileo was condemned for flirting with heresy and sentenced to house arrest for the remainder of his life. Human beings prefer to think that the universe revolves around them. As a result of being at the top of the heap on Earth with ever fewer predators to thin their numbers, Homo sapiens multiplied and migrated around the planet. Slowly at first, and then all at once, their numbers grew. It took 200,000 years for their population to reach 1 billion, but only 124 years more to reach 2 billion. A mere 33 years after that, they reached 3 billion. Now their numbers are approaching 8 billion. In 64 years, the projection is 11 billion. This population explosion, combined with increasing consumption habits, has begun taxing the Earth's carrying capacity to feed, clothe, shelter, transport, and otherwise provide for such burgeoning masses of humanity. Worse, the Earth's carrying capacity itself is being reduced as its climate warms and crop yields are adversely affected. The same burning of fossil fuels that liberated humans from their reliance upon muscle power vastly improved their productivity and allowed for such dramatic population increases. Also increased the insulation value of the planet's atmosphere through the emission of long-lasting greenhouse gases. The result has not been good for the Earth's species, which have been going extinct at a far greater pace than the background extinction rate, up to 10,000 times greater than the historical average. Will Homo sapiens also go extinct? Climate scientists have been sounding the alarm in earnest about climate change since the mid-1980s, and yet each year humans continue to burn more fossil fuels and emit more greenhouse gases than the year before, with the notable exception of 2 breather years during the Great Recession and the recent pandemic. As a result of that track record, the near-term prospects for civilization have significantly declined. Indeed, humanity may ultimately prove to have been a cancer on the face of the earth during the former's relatively brief run of 200,000 years, as compared with Homo erectus, which lasted for nearly 2 million years. Cancer cells, too, multiply beyond measure until they destroy the life-sustaining ability of their host. Despite their inflated self-image, Homo sapiens' lasting legacy may be as an aggressively terminal planetary disease for most of Earth's life forms, including themselves. But that may be an overly harsh assessment. Human beings may have simply been fulfilling a brief but necessary role in a much larger process. As has been shown, there is even a place for mass extinctions in the advancement of increasing complexity. Just as the 5th mass extinction in Earth's history paved the way for the rise of Homo sapiens, it is interesting to speculate about what could follow the next mass extinction. While it may be as difficult for humans to fathom what comes next as it is for a chimpanzee to fathom us, we are given some things to know. First, great strides have been made of late in the field of genetic engineering. Not only has the human genome been mapped, gene editing is a present possibility with CRISPR technology, which is available for purchase online. Among the admittedly arguable potentials of this new technology is the ability, for the first time in Earth history, to bypass evolutionary processes in engineering superhumans, humans that are not only protected from genetic health deficits, but cognitive deficits as well. By unlocking the potentialities of the brain, humans could be engineered, which would make Einstein appear slow by comparison. Surely they would engineer their succeeding generations to be incapable of reproducing with mere mortals, just as the latter would resist mating with intellectually disabled people. They would, in effect, engineer a new species with the innate resources to reverse climate change, control population growth and consumption, eliminate nuclear threats, process pollution, and otherwise manage what is increasingly becoming unmanageable for Homo sapiens. But why limit what comes next to organic life options? Great strides are also being made in the field of artificial intelligence, also known as AI. Society is on the threshold of machines which can labor more efficiently and less expensively, drive cars more safely, and play complex strategy games more successfully than humans. Already, social media employs AI algorithms that understand humans better than they understand themselves. A hybrid of genetically engineered superhumans implanted with access to AI technology would be a formidable combination. But again, why allow for organic limitations at all, especially if interplanetary ambitions are a feature of the next level of complexity? Humans in particular, and organic life forms in general, have evolved within a very narrow environmental envelope of temperature extremes, atmospheric conditions, water, nutrient, and microbe availability, gravitational needs, radiation protection, and a host of other needful conditions which are a challenge to reproduce in space and on other planets. Inorganic systems of superior intelligence made possible by AI do not require liquid water to survive, not to mention much else demanded by organic life. Plus, the former can more easily go dormant during long space travels until the time comes for reactivation. Advances in AI and genetic engineering, along with existential threats like climate change, are relatively recent developments. Hence the need for an update such as this to reconcile these changes with the unchanging purpose of existence. While the end of the human species is an unsettling realization, akin to receiving a terminal diagnosis on a personal level, a transcendent hope may be found in a new and better day dawning on the unbroken march of increasing complexity. We all know that we are going to die sooner or later, but we find some measure of comfort in the succeeding generations who will follow us. We are part of this larger continuity, which will go on long after we are gone. But even the end of our species is not the end of existence. Existence will not only continue, it will do so in more marvelously complex expressions than we can imagine, given our limited capacities. That we cannot know certain things is a sure sign that we are not the be-all and end-all of existence. We are a wee part of a great continuity that began with a bang long before us and will continue long after us in forms of ever-increasing complexity. If humanity's inability to manage existential threats like climate change nevertheless serves to further the purpose of existence, then we can face our end because it is not the end. In the words of John Lennon, everything will be okay in the end. If it's not okay, it's not the end.